horizontal asymptotes. So these are AKA end behavior, okay, from polynomials. Basically, what is happening at the end, right? So for rational functions, it generally kind of has these like boomerang shapes. So basically, we just want to know like where are we leveling off to? Okay, where are we leveling off to? And generally, it's the same place. So it might be like 3. And if I have a vertical asymptote, then essentially these are our guidelines of what our boomerangs are going to look like. Okay, and we'll find out here that yes, we can even have like a slant asymptote. If we also have a vertical asymptote, then we have just more narrow boomerangs, if you would. Okay, so when I say end behavior, again, we mean at the end, what's going on? Where are we going off to? That's what we mean by horizontal asymptotes, aka end behavior for a rational. So the line y equaling b is a horizontal asymptote, right? Because y equaling, that is a horizontal line. So for the graph of f of x, if f of x approaches d as x approaches positive or negative infinity, this right here is just a long-winded way to say left or right. Well, I actually have it kind of backwards, right? Left would be negative infinity and right would be positive infinity. Positive infinity is right, negative is left. So given I have a rational function, f of x equals ax to the n over bx to the m, well, we are looking at the degrees. Okay, we're looking at the degrees of the the exponents, the degree of the polynomial. Degree n and degree m. N and m. Yeah, so we have 3 options. If your bottom heavy degree, n is less than m, then your horizontal asymptote is y equaling 0. This is if you're bottom heavy. Degree bottom heavy. Okay, the reason for that is because if I am degree bottom heavy, then essentially I might have something like 1 over x. Right? Because up here, that's x to the 0 over x to the first, which is 1 over x. So if x is getting big, right, if x is going left or right, then I could have 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 10, 1 over, 100, 1 over 1,000. So then that's 1.5, 0.3 repeating, 0.25, 0.2, and then 0.1, 0.01, and then 0.001, and then hopefully you get where I'm going with this, right? The overall number goes to 0. So if you're degree bottom heavy, then you have a horizontal asymptote of y equaling 0. If the degrees equal each other here, then it's the ratio of the leading coefficients. Okay, y equals a over b. That's right there. The ratio of the leading coefficients, just a over b, if they equal. And if we are top heavy, if we are degree top heavy, then there's no horizontal asymptote. Okay, so these 3 things right here, you might want to put on your note card. Okay, but also if you have a graphing calculator, I mean, you can just graph and look. So there is a caveat, of course, because that's what makes math hard. It's not that math follows its own rules, it's just that its rules has exceptions. So if n is exactly 1 more than m, so if you are top heavy by 1, so let's say I have 3x squared over x, example, then we have a slant or oblique asymptote. Think of slant, oblique, your side core muscle, your side abs, those are your obliques, right? So it's a side or slanted asymptote. So that is this thing right here. Okay, we don't really talk about them a whole lot in this class, but they are always of the form y equaling mx plus b because they're linear lines, right? They're linear lines over here on the left. It's just a linear line, an invisible linear line of this order. Okay, so for A, B, and C, I'm just going to identify the leading terms and the degrees. So here, this is degree 2. The denominator has degree 3. So I think of this as bottom heavy. So I know automatically that this is y equaling 0 as my horizontal asymptote. Again, and why do I know that? Again, because I am degree bottom heavy. That's the rule. If I were to graph it, I mean, we'd have all this stuff, but essentially, oops, if I could draw, my boomerangs would eventually look like the y-axis. We would just get closer and closer and closer to the y-axis. Then again, let's get a new color. Look at the leading terms. Again, remember, just because it's in front does not necessarily mean that it's the leading term. So I have a negative 2x squared and a 3x squared. So the top is degree 2, or numerator. The denominator is also degree 2. So that rule says if they equal, that is the ratio of their leading coefficients. So here, the horizontal asymptote is y equaling negative 2/3. And what, like, it is that easy. You just follow, I don't know if that's easy because it's a rule, but it's something you can write down on your note card. So negative 2/3. So if this is -1, we'll call negative 2/3 right here. So again, we would just have these boomerangs that flat line like this, okay? It would just eventually, this isn't the exact graph, forgive me. They would just flatline to negative 2/3. And then here, the last one, looking at the leading coefficients. The numerator is degree what? 2. The denominator is degree 1. It's invisible, but it's there. So this means we have a slant asymptote. How do we find slant asymptotes? Your favorite pastime, polynomial division. Find slant asymptotes with polynomial division. One reason why we learned polynomial division. This one, we can use synthetic division because it is just x minus 1 as the divisor. So we can have 1 on the outside and then 1, -3, 5 on the inside. Drop the 1 to get the ball rolling. Remember that your check mark is multiplication. So 1 times 1 is 1. Add down, -2. 1 times -2 is -2. And then we add down, so that's 3. So keep in mind, this represents your x squared, excuse me, your x, your constant, and your remainder. So this says we have a slant asymptote of y equaling x minus 2. And we get to ignore the remainder because it's too small, right? It would technically be, let me put it in the cloud, plus 3 over x minus 1. But this goes to 0 for the same reason as it being degree bottom heavy. Okay, so you just ignore that portion of it. Okay, then we'll pick up with graphing rational functions.